What I am going to speak is about is quite classical in quantum theory. I begin with the standard normal distribution with which all probabilists. This is the first continuous distribution which any statistician or a probabilist comes across. Normal distribution. It is a probability density defined on the real line given by 1 by root 2 pi e to the power minus x squared over 2. This was first arrived at by De Moivre in his analysis of the binomial probability distribution, but he did not know what this factor was. Later Stirling's formula was discovered, and then the correct constant was obtained, and this was polished later by Laplace, and then later by Gauss in what is called the theory of errors. So this is combinatorial. This is general theory of errors, the principle of least squares analysis. Then in Rn, the normal distribution was first introduced by Lagrange in Rn. He analyzed De Moivre's problem in what is called, here he used it for binomial distribution, and he tried to generalize the argument for multinomial distribution and arrived at the normal distribution in Rn. So in Rn, the most general Gaussian density or normal density is 1 by 2 pi to the over n over 2 determinant of sigma root into exponential minus 1/2. There is a mean vector for that transpose sigma inverse x minus m. This is a probability density function in Rn. If you take product of n copies of that and apply an affine linear transformation to the variables, translate by m and apply a square root of a linear transformation of if sigma equal to L transpose L, then you apply L, first you translate and then apply L. So take n copies of that and make a transformation, x goes to L applied to x plus m, then you will get this density. So starting from 1, the affine linear group acts and you get thereby all the normal densities. I am emphasizing this fact because later on in quantum Gaussian states we want to see what is the appropriate group, like this affine linear group, what is the appropriate group for Gaussian states. Professor Simon is here, he is an expert on quantum Gaussian states. So what I am going to say is very well known among physicists. Now the Fourier transform of this is e to the power minus t squared over 2 for this measure. And the Fourier transform for this is e to the power I m transpose t minus half. There is a quadratic form here, t transpose sigma t. So, if this is sigma inverse here in the Fourier transform, it becomes sigma. Now, to study Gaussian quantum states, quantum Gaussian state, here you consider this as a probability distribution of n random variables, x1, x2, etc., xn. Multiplication by each of the coordinates can be thought of as a self-adjoint operator. So, these things, multiplication by these give you variables q1, q2, etc., qn, which are self-adjoint operators, and the joint distribution of these random variables is exactly equal to this. But classical quantum theory begins with q1, q2, etc., qn self-adjoint operators and p1, p2, etc., pn. They are also self-adjoint operators. There are 2n variables. This is position variables, which is the same as in classical probability, but because of dynamic mechanical problems, you also look at the associated momentum variables, and you want to look at the joint distribution of all these objects. Now, these are self-adjoint operators, but they don't commute. These self-adjoint operators commute, these also commute, but if you take QRPS, this is equal to I delta RS, which gives the Heisenberg-Lie algebra. Now, there is a Fourier transform theory already in Rn. So, what is the Fourier transform theory for this? That means, roughly speaking, or anything concerning a quantum system is enacted in the stage of a Hilbert space, complex Hilbert space. Probability distributions are replaced by what are called density operators. Density operators, which means rho is a positive operator with trace rho equal to 1. Random variables are replaced, as you saw in this example. Random variables are replaced by what are called observables, and observables are self-adjoint operators. So, self-adjoint operator, they can be unbounded or bounded operator, and they are called observables in quantum theory. If this has a spectral resolution, x is equal to lambda px d lambda over the real line, then trace rho px E, if E is a Borel set in Rn, you consider this. This is a probability measure, not in Rn but in R, because this is in R. Probability distribution of x in the state R. In the state rho. Now, for a probability measure mu on Rn, if you have a probability measure mu, then you can consider e to the power I t dot x d mu x over Rn, that is the so called characteristic function or Fourier transform. And this correspondence mu to mu hat is a bijective correspondence, and also there is a topological correspondence. If mu n converges to mu weakly, mu n hat will converge to mu hat in what is called the UCC topology. Before Lyapunov, the central limit theorem and all other kinds of limit theorems were proved more or less either by direct combinatorial analysis or by what are called moment method, and it was Lyapunov who exploited this characteristic function and proved the central limit theorem of probability theory. Now they are only about the q variables, but when you have both the q and p variables and they don't commute, what is Fourier transform and what is convergence? And then I have written here the formula for the Fourier transform of the distribution, and correspondingly we want to define a Gaussian state, and then what is the Fourier transform, the quantum Fourier transform of the distribution. But the main important point is the kernel which you are using to integrate to go from mu to mu hat is an exponential kernel, which is also a homomorphism for fixed dx in t and for homomorphism in t in fixed dx in fixed t. So it is multiplicative in x and it is multiplicative in t. So if I have a state rho, what is meant by Fourier transform? Roughly speaking, if I imitate this, I should consider operators of the form e to the power I sigma xj pj plus yj qj, where these are the CCR variables. When this setup holds, one says the canonical commutation relations hold, so that is called CCR. For CCR variables, one would, here the integration, the probability of E is obtained by trace rho multiplied by this. So if you want the mean, you will integrate this, you will substitute this distribution here, namely trace rho p here, and that will become trace rho x. So the mean value will become trace rho x, or better to write it x rho, because this is a good operator, this is an unbounded operator, and now that should be traceable and you can take trace. That is the mean value. So the Fourier transform will now look like this is e to the power I times some operator, but this is considered as an observable or a sulfur joint operator. E to the power I times that is a unitary operator. So you can imagine the trace rho of this, trace rho, and you can call this as rho hat of the variables x, y, or you can combine the two and call it x plus I, y, so that you have n complex variables. So whether you can construct such a Fourier transform and execute the same classical program with this kind of Fourier transform. That is the basic problem. Now to handle these unitary operators, you want to still have this kind of homomorphic property of the kernel which enters the Fourier transform. So, what is that kernel? That evolved through the researches of Weyl and Wigner. So, to do that, you have to first describe this in terms of unitary operators, and that can be done in a nice way with a more modern notation than is usually done in the physical literature. So, in order to execute that, I look at L2 of Rn and then I introduce what are called the coherent vectors. These coherent vectors are very interesting vectors. They come in all kinds of places, not only in quantum theory, but also in modern financial mathematics for some reason. So, I introduce functions Ez of x. This is equal to exponential of sigma zj xj. Xj is not real part of zj. Z is complex variable and x is the real variable. It is not real part of that. Minus zj squared over 2 minus xj squared over 4 into 1 over 2 pi to the n over 4. You see, if you take 1 by 2 pi n over 4 exponential minus xj squared over 4, that is simply the square root of the normal density. The normal density is a probability density, but we are going to do everything in this Hilbert space. The square root of the normal density is an element of the Hilbert space. So, that is what you get. If you forget the j, e to the power zx minus z squared, if you consider that as a function in z and expand in power series, the coefficients of z power n, they are the Hermite polynomials. So, that is the generating function of the Hermite polynomials. So, it is natural to consider this function, and if you analyze these properties, many of the classical properties in the theory of Hermite polynomial, they are all contained in the following equation. Now, I will use the wrong inner product f. I will write like this, and this is integral f bar g, or if it is a discrete variable, summation f bar g. The bar is in the first variable and in the second variable there is no bar. So, this is conjugate linear in the first and linear in the second. So, I will adopt this notation. So, if you compute Ez prime, then this is equal to exponential of z prime. This is in Cn, this scalar product is in Cn, namely sigma zj bar z prime j, summation over j. Whereas this is in the Hilbert space. These are called exponential vectors. Exponential vectors. And to make it a unit vector, you write C of z equal to e to the power minus half norm z square into E of z. If I write like this, it is the element of the Hilbert space, But if I write like that, then that is an element of the dual, that it is a linear functional on the Hilbert space. So these are the so-called bra vectors and they are the ket vectors in the standard Dirac notation. This is a unit vector. The exponential vector normalized, this is a unit vector. Unit vectors give rise to pure state, namely the one-dimensional projection on the ray generated by that. So, if you take the ray generated by CZ and then consider the projection, and that projection can be expressed in the following way. You can consider this as a column vector, so CZ, and then you put here the ket vector CZ. This becomes a one-dimensional projection. This is column vector multiplied by row vector gives a matrix or an operator. In the same way, this is linear functional. So, if you put a ket vector here, this becomes a scalar times this. So, that is the projection, right. So, if you use the Dirac notation, this gives you a projection, and because it is a unit vector, this gives you a one-dimensional projection and its trace is 1. So, this is greater than or equal to 0 and trace equal to 1. You can flip for trace and you get trace equal to 1. So, that gives you the coherent vectors, the unit vector. These are called coherent states. Coherent states. Because this projection which is one dimensional, it is a positive operator of trace 1, they also give rise to states, they are called pure states. They are examples of pure states. There is a theorem which is frequently used in quantum theory. I think it is due to Sudarshan and some others too whom I don't know, but it was from the notes of Professor Sudarshan I learnt this interesting formula. It is very useful in computing traces. Namely, if you take this coherent vector and take this projection CZ, and then you integrate dx dy, n variables, double integral, and then put here 1 by pi power n, this is equal to identity operator. So, this is a formula due to Sudarshan. Which I will make use of in one place in the course of the lecture in computing the simplest Gaussian state, the Fourier transform of the Gaussian state. Now, once you have these vectors, these are the exponential vectors. Now, I want to strike at the exponential which I mentioned earlier, exponential of the sums of the position and momentum operators. So, if I write W of U applied to Ez, this is not normalized, this equal to e to the power minus half norm z square minus the scalar product ZU, UZ in the same order, and then you translate the exponential Ez plus U. So, this is an operation on the exponential vector which translates this exponential vector and puts an additional scalar factor. Once I do this, then you can check that this preserves scalar products. On the set of exponential vectors, WU preserves scalar products. Scalar product on the set of exponential vectors. And the exponential vector, the whole family, they are total. They are linearly independent, that is, any finite number of them is linearly independent, and total, that is, they span linearly independent and spans the Hilbert space H. So, closed linear span, closed L2 Rn in this case. And they preserve scalar products here, and therefore WU determines a unique unitary operator. So, you get WU is a unitary operator. And then you can compute everything directly if you use WV. This is equal to e to the power minus I, imaginary part of UV into WU plus V. And in particular, each WTU, where T is real, T to this tells me is a one parameter unitary group. One parameter unitary group. So, WTU, this can be expressed as e to the power minus ITPU, where PU is a self-adjoint operator. PU, which is the stone generator of the group, is a self-adjoint operator. So, it is an observable. So, it is an exponential of a self-adjoint operator. Now, if U is equal to x plus Iy, and I write here, you choose the canonical basis Ej in Cn, which is 0, 0, 0, at 1 at the jth place and then 0. And then write here Pej into 2 to the power some normalizing factor.
U is unit vector, this U is.
Huh?
U is unit vector?
No, U is an arbitrary for a.
Then why is that group?
I just came to my mind and I used that symbol. There is nothing wrong. T to WTU is a one parameter unitary group for every U in Cn. U, V, W are all vectors, not necessarily unit vectors. Pej, you have to normalize it with I thought I had written it in the notes. Either 2 to the power minus Pej multiplied by 2 to the power minus half. If I call this as Pj, that is a sulfur joint operator, and Qj equal to minus 2 to the power minus half Pij J, then the Pjqj is a CCR. So they come as part of this exponential. Okay. And Wu because of this can be written in the following form. Wu in terms of these the stone generators at a canonical basis which give rise to the CCR, I can write it as exponential minus I root 2 into sigma xj pj minus sigma yj qj. So they come from a group representation. So all linear combination, they come as representing elements of the Lie algebra, and this you can even prove. Okay, I will come to the exact formula soon. This can be considered a sulfur joint operator, but I use the same notation. Even though it looks like a formal linear combination, it is actually its a closure which comes, and that is sulfur joint, and exponential minus I root 2 times this. So I can use this legitimately for defining Fourier transform. The Weyl operators can be legitimate where u is equal to x plus iy. U equal to x plus I. And it is interesting, it is an interesting exercise. If you make a small change here, namely, if I change Pj, I will write here Pjs, that is equal to okay, I think that is equal to 2 to the half Pj, which comes here. If you put 2 to the power half, then for Qjs you must put here 1 over 2 to the half Qj. Then again this is a Qjs. This transformed ones also obey CCR, and I put S here to denote Schrodinger. If you do this, then Qj is nothing, Qjs is nothing but f applied to x equal to xj qj, xj fx, and Pjs applied to f at the point x is 1 over I delta by delta xj f. And how do you define this? You define on the Schwarz space S of Rn and then close. That gives you the sulfur joint operators Pjs and Qjs. There is only one scaling factor which is different. So Pj, Qj, they can all be considered on the common core, all the linear combinations of Pj Qj have a common core in the Schwartz space. So, they become mathematically eligible operators, and then I use the same linear combination as the symbol for that closed self-adjoint operators, and so exponential minus I is a unitary operator, and that coincides with the Weyl operator. But the Weyl operator directly on coherent vectors is a very nice translation action. This is basic to the Fourier analysis. Okay. So, now I can define Fourier transform. I can define Fourier transform. So, you can call it a quantum Fourier transform or Wigner-Weyl Fourier transform, quantum Fourier transform. Rho hat of z equal to trace rho multiplied by Wz, where W dot is the Weyl operator. The Weyl operators, they are not like exponential, they are like exponential modulo a twist. This is what you should remember. And so, the correspondingly the Fourier transform also undergoes, the whole theory of Fourier transform also undergoes a corresponding twist, right. So, you have to keep in view that Wz prime is not Wz plus z prime, but it is e to the power minus I imaginary part, there is a multiplier here for the projective representation at Wz plus z prime. And we need some basic important properties of this Fourier transform as well as the Weyl operators to do our analysis. Right. This map, note that rho hat z is rho hat 0 equal to 1, z to rho hat z is continuous in Cn, and it has a positivity property, what is called the quantum Bochner property, right. 2 quantum Bochner positivity property. And it is proved exactly as in classical measure theory, namely consider any operator of the form Cj these are the exponentials now Zj. Then x adjoint, I use the physicist notation, x dagger means x adjoint. X dagger x is a positive operator. Rho is a state. So, trace rho x dagger x is greater than or equal to 0. which means what? It means sigma C j bar C k trace trace rho W Zj dagger Zj adjoint W Zk trace of this summation over Jk greater than or equal to 0, which means sigma Cj bar Ck trace rho, but Wzj inverse, that is W minus Zj. W minus Zj, Wzk, that is Wzk minus Zj multiplied by e to the power I times imaginary part Zj Zk greater than or equal to 0. Which means, if you define k of z prime to be equal to e to the power I imaginary z prime multiplied by trace rho hat z, okay. This is nothing but rho hat, that is the Fourier transform of z prime minus z. This is the kernel and this is a positive definite kernel. Positive definite kernel. In classical measure theory, this part is absent. Only if this is positive definite, a function is positive definite and continuous, it is the Fourier transform of a measure. But now you have this twist which comes here, and this twisted, and this kernel should be positive definite. If it is a quantum Fourier transform of a state, this property should be fulfilled. And the quantum Bochner theorem is that its converse is also true. So, you have the quantum Bochner theorem this is a very basic result. Quantum Bochner theorem let z to phi z be continuous and let k z prime equal to e to the I imaginary part z prime minus z, imaginary part of the scalar product z prime phi z prime minus z be positive definite. Positive definite. Then there exists a unique state rho, such that phi is equal to rho hat. That is the quantum Bochner theorem. And the proof is also very simple, because whenever you have a positive definite kernel, you can use the GNS principle to construct a Hilbert space. And using this translation invariance which comes in this part, but because of the twist, instead of an ordinary representation, you will get a projective representation, with respect to which the state rho in the Gelfand space can be constructed. So, and then the W's the uniqueness, everything will come out. That is, from the positive definiteness you will get a Hilbert space, and the translation will give you a projective representation, and you will get a vector psi, not vector, you will get a positive operator rho, and then you can you will first get a vector psi, but from that you can extract the required positive operator rho to express it as the expectation value of rho at the representation. But you will, so the proof is a combination of GNS principle and that projective representation is unique, plus the Stone-von Neumann theorem. These two have to be combined to get a proof of this. And the Stone-von Neumann theorem in the following form. That is a property of the Weyl commutation rules. Namely, I forgot to put down early, that what I say now should have been told earlier. Going back to the Weyl representation, you consider a general representation gamma for Cn obeying gamma z prime equal to e to the minus I imaginary part gamma z plus z prime, and z to gamma z strongly continuous. Of course, these unit gamma z are unitary, these are unitary, so you can put weak or strong continuity, continuous, weak or strong, both are same. Any solution of this is always unitarily equivalent to WZ tensor product identity. Some auxiliary Hilbert space, you take tensor product and put identity, and these are the only solutions. Whereas this single copy Z to WZ, that is irreducible. This is irreducible, projective, unitary representation. And this theorem holds. This is another way of stating the famous Stone-von Neumann theorem. So, in this proof, this translation invariance here modulo a scalar factor of modulus unity, that will give you some projective representation, and that projective representation multiplier will be this. So, by Stone-von Neumann theorem, it has to be of this form, and because of this tensor product I, you will get, instead of a vector, finally you will get a operator rho, right. So, that is the proof which you can easily construct from these small hints. So, once you have the quantum Fourier transform, we can, I need one more property of the Weyl. So, what are the properties of Weyl? Z2WZ is a very important, that is the exponential required for CCR. As I told you, it is irreducible, unitary, projective, and the multiplier is e to the minus I, imaginary part ZZ prime. And then you want to know how does it transform. If you conjugate by another W alpha, WZ, W alpha inverse, that will be e to the power minus 2I times imaginary part alpha Z WZ. Now, the Stone-von Neumann theorem yields something more now. Namely, suppose I consider a transformation of the Z to Z prime, which is additive, and L preserves the imaginary part of Z1, Z2. That is, imaginary part of Z1, Z2 is also the imaginary part of LZ1, LZ2. And then real linear, additive instead of that real linear. They are the symplectic transformation. But in R2n, because I am separating the variables, L can be visualized as L11, L12, L21, L22, and then you have xy, and you call this as x prime, y prime. Then you consider the transformation x plus iy goes to x prime plus iy prime. And if it preserves the imaginary part, that means the transformation L has the property L 0 minus I 0, L transpose equal to again 0 minus I 0. That means all these L come from SP 2n R. Then you see, you note the following. If you consider the Weyl operator on L acting on Z in this way, this is also another solution to the, because it preserves the imaginary part, it is also another solution to the Weyl commutation rules. But that is unique up to a unitary conjugation. So, whenever there is the symplectic L, that means there exists a unitary transformation gamma L such that there exists gamma L unitary such that WLZ equal to gamma L WZ, because the two are equivalent, gamma L, gamma inverse, gamma L unitary. And the irreducibility shows that gamma L is unique up to a scalar multiple of modulus unity, and you will have gamma L1, gamma L, gamma M for any two such symplectic matrices, that is some sigma L m, there is a scalar there which you cannot dispose of, such that this is gamma L m. And this has an important effect on the Fourier transform, which will be used in the analysis of Gaussian states later. In our second lecture, we will do this. So, if I choose, if I have a state rho, if rho is a state and u is a unitary operator, then u rho u inverse is also a state, right? U rho u inverse is also a state. Now, if I use that gamma L rho gamma L inverse, that is a state. But what is the quantum Fourier transform or Wigner transform at the point Z? This is a trace of this multiplied by Wz. So, this is trace, and that gamma L can be brought to the other side. So, this hat Z equal to trace rho gamma L inverse Wz multiplied by gamma L. So, but gamma L has the property, on the Weyl operator, this is trace rho W L inverse Z L inverse Z, which is equal to rho hat L inverse Z. So, gamma L rho gamma L inverse, its Fourier transform is Fourier transform of rho at L inverse Z. This is something similar to, namely, if you have a measure mu and if you have mu hat of that, the Fourier transform of that, then if you make a linear transformation L inverse and then compute Z, this L you can push it there, right, but it will come not L Z, but L transpose Z T, because this is e to the power I t dot x d mu L inverse, which is integral e to the power I t L inverse L of x d mu, and that will become L can be taken to L transpose here. So, this is mu hat at L t, L transpose t. So, you have a similar, a linear, a symplectic transformation on the state rho will affect in the quantum Fourier transform, the variable inside will be changed. So, we will make use of this property. All the properties I need for analyzing a Gaussian state, I have stated now. So, we will take up the actual Gaussian state theory in the next lecture, right. Thank you.